Two more things we're going to be able to calculate with line integrals over vector fields are going to be flow and flux. So this is going to calculate how much of something is moving along a curve or moving across a curve. So the flow is how much is moving along the curve. And this could be how much water, it could be how much electricity, whatever that vector field represents. So we have three different curves in this graph here, C1, C2, and C3. So the curve C1, everything for C1 is happening in exactly the same direction as the vector field. So curve C1, we're going to find that this curve is all flow and zero flux. All of the water or the electricity or whatever it is moving in exactly the same direction as the curve C1. C2, on the other hand, is going to be all flux. Flux is talking about how much is moving across C. So how much water or how much electricity. So think of that C2 as being like a net in the water, and all the water is passing through C2. So this curve, if we do this calculation, what I'm going to show you how to do, this is going to end up being all flux and zero flow. But then C3 is kind of on a diagonal, and it's going to be a mixture of both. So we're going to have non-zero flow and flux. Flow and flux are both calculated with a line integral, but different kinds of line integrals. Flow is going to be calculated by the line integrals over vector fields that we already know how to do, these f.dr. So remember, we can calculate these two ways. Our basic way was to make this our vector field of our curve parameterization dotted with the derivative of our curve parameterization. That was if it was not conservative vector field. If it is a conservative vector field, we have that really nice fundamental theorem of line integrals that makes it really easy. Okay, so we can calculate this as the potential function at the endpoint minus the potential of the start point if f is conservative. So these are just going to be a repeat of the examples that we did in section 14.3. All right, so let's calculate the flow of this vector field, f equals negative y comma x, over the unit circle in counterclockwise orientation. All right, so if we knew that this was a conservative vector field, then we would be able to find this using the fundamental theorem of line integrals. A quick check is going to show you that the curl is not equal to 0. In fact, if you want to do this kind of in your side, you want to pause the video, the curl of this vector field ends up being 0, 0, 2, which is not equal to 0. So this is not a conservative vector field. Okay, so all this means is that we're going to have to do our line integral the old-fashioned way. So remember, we do this calculation f.dr. We're going to parameterize that curve from A to B. We'll find our vector field, plug in our parameterization, and dot that with the derivative of our parameterization. All right, so let's parameterize our curve. It's the unit circle. We know how to parameterize this one. This is going to be cosine t comma sine t, and t is going to go from 0 to 2 pi. All right, so for our line integral, we're going to plug our parameterization into our vector field. So our x component is cosine t. That shows up in our vector field in the y component. So we're going to put cosine t there. And then our y component for our parameterization is sine t. That's going to go up front in the vector field in the x component. All right, so let's find our integral. We're going to integrate from 0 to 2 pi. We're plugging in our parameterization into the vector field. We're going to get negative sine comma cosine from the work we did up above. And we're going to dot that with the derivative of our parameterization. So looking at my r function there, derivative of cosine is negative sine. Derivative of sine is cosine. Now we got to find a dot product. This one is looking like it might be pretty easy. So I've got negative sine times negative sine gives me a positive sine squared. Dot product, so we add. Cosine times cosine is cosine squared, which is a lovely integral that boils down just to 1. Sine squared plus cosine squared equals 1. All right, so that's a very easy integral to do. 1 dt, we're going to find the antiderivative and get t. We'll evaluate that from 0 to 2 pi. Just plug in t equals 2 pi. minus 0, and we get a positive 2 pi. All right, so that is the flow of this vector field along that curve. So here I've had Mathematica graph our vector field for us, and it's a rotational vector field, is rotating counterclockwise, and our circle orientation was rotating counterclockwise as well. So all of this flow, electricity, water, whatever this vector field is representing, is kind of flowing in the same direction as our curve. So it makes sense that we got a positive flow for this curve.